My project was about the chemistry of glowsticks. The reaction within a glowstick is between diphenyl oxalate hydrogen peroxide and dye, which yields trichlorophenyl carbon dioxide and dye in an excited state. For the reaction in a glowstick to take place, the reactants are first separated before you crack the glowstick, which prevents them from mixing prematurely. Once you crack the glowstick, the reaction is allowed to take place, thus emitting the glow of the glowstick. Here you can see the reaction taking place in an actual glowstick. Part of the chemistry behind glowsticks involves a topic called chemiluminescence. In this process, the diphenyl oxalate is oxidized by hydrogen peroxide, which produces an unstable compound, which is called 1,2-dialzetadione. And this decomposes into carbon dioxide, which also releases energy because it is so unstable. The energy is absorbed by the electrons in the molecules of dye, which put them in an excited state. When they go back to their ground state, they lose this excess energy in the form of photons of light, and this is the glow of the glowstick. This reaction cannot be classified as exothermic because heat is not emitted. However, it is referred to as exergonic because it releases energy instead. The next topic about the chemistry of glowsticks is reaction rates and temperature. There is a direct correlation between increasing the temperature and increasing the rate of reaction, and this is in terms of collision theory. With collision theory, particles can only react when they can collide, and if you add heat to the solution, the particles will move faster. Once the speed of the particles is increased, there is also a higher potential for collisions amongst the particles, and therefore a higher rate of reaction. Activation energy and potential energy are both also part of the chemistry of glowsticks. On this graph, the number of particles is on the y-axis, while energy is on the x-axis. The blue graph will show the activation energy at a low temperature, while the red graph will show the activation energy at a higher temperature. As you can see, the activation energy is nearly twice as much for the high temperature. This tells us of the direct correlation between an increase in the number of particles that reach the activation energy and an increase of the rate of reaction. My chemistry demonstration was looking at the correlation between the reaction rate and temperature for glowsticks. I took 3 glasses of water, one with cold, one with room temperature, and one with hot water, and I put a glowstick in each glass to compare the brightness of each. The glowstick in the cold water emitted very little glow, which means its rate of reaction was slower under the cold circumstances. The glowstick in the room temperature water emitted a normal amount of glow, as it was more of a control for this demonstration. The glowstick in the hot water emitted a very bright glow, which means that its rate of reaction was very fast under the hot environment. I can therefore order them in terms of both increasing brightness and, directly correlated with that, increasing rates of reaction. This demonstration does not only tell us about the varying glows between different temperatures. Because the glowstick in the hottest water had the brightest glow and therefore the highest rate of reaction, its glow will last the shortest because the reaction will be complete sooner than that of the glowstick in the cold water. I can therefore order the glowsticks in terms of decreasing length of glow, which is also the order of increasing reaction rate. Here you can see a time lapse of the actual demonstration. The cold water is on the left and the hot water is on the right. As you can see, as time goes on, the glowstick in the hot water grows to be very bright, while the glowstick in the cold water decreases in brightness. This photo was taken a few hours after the experiment was started. As you can see, the glowstick that was in the hot water on the far right is done reacting and has no glow left. The other 2 glowsticks, which were in cooler water, still have glow left because their reaction rate was not as fast, and therefore their reaction is still occurring. Here you can observe better the difference in brightness between the different temperatures of water. So what can you take away from this demonstration? If you want your glow sticks to last longer, pop them in the freezer. And if you want them to be really, really bright for a shorter amount of time, heat them up.